Now let's talk about how we would calculate the pH of a buffered solution. So let's say that I have a buffer solution in which the concentration of HF is 1.0 molar and the concentration of NaF, right, so that contains that F minus ion, that's the conjugate base of the HF. The concentration of NaF is 0.5 molar. We need to find the pH of this solution. Now, back in chapter 7, we talked about a strategy for calculating the pHs of various aqueous solutions. And this strategy always starts by asking ourselves, what are the major species that you would have in your solution before any acid-base reactions occur? The advantage of writing out the list of major species is you can use that to identify what type of a problem you're working with, and also, if necessary, write out reactions that control the pH that your solution has. So I want you to take a moment to think about what are the major species that you have in this solution, and put in your answer to this question. And on the other side of the question, we'll go over it together. All right, having given you an opportunity to work through this question, let's talk through the answer together. When we write the list of major species in solution, it's important to keep in mind the word major and what that word is telling us. So the word major means that it's going to be present to a large extent in your solution. Now, in the case of our weak acid HF, this does not dissociate to a very large extent in water. You could calculate the percent dissociation if you want, and you'd find that it's somewhere on the order of about 1%. So I would not consider H plus and F minus to be major species in this solution, right? There's a very small amount of that present. 99% of the HF remains in the form of HF, and so that would be considered a major species in solution. So key point on this is keep weak acids and bases together. So that gives us HF as a major species. Now, for our NaF is a soluble ionic compound, and so we've talked about how those dissociate completely into ions in solution. And so you will not have NaF in solution. You will have dissociated Na plus and F minus ions in solution. That's the major form that the NaF shows up in. And so another rule for writing the list of major species is that we will always dissociate any soluble salts. In addition to that, it's beneficial to also just extend this rule out a little bit more so that you'll be able to use it a little bit more with a little bit more variety when we look at other problems. You should also completely dissociate any strong acids or strong bases because those break up 100% in solution. So if you had, let's say, HCl, that's a strong acid. It does not exist in the form of HCl. 100% of it breaks up to H plus and Cl minus. So you would also dissociate any strong acids or any strong bases. All right, so with that rule in mind, our list of major species in this solution is as follows. HF is a weak acid, so we keep it together. NaF is a soluble ionic compound or a soluble salt, so we break it up into Na plus and F minus. And then in any aqueous solution, water is always a major species, so we'll add that to the list. And there we have it. That's our list of major species. The correct answer here is B. Now, having written the list of major species, let's now talk about how we would find the pH of this solution. So now that we know what the major species are, we've identified that this solution is a buffered solution because you contain in this you have in this solution a weak acid, that's HF, and you also have its conjugate base, F minus. You can make a little note of that here. This is a buffer. Now, by identifying that you have a buffered solution, that will dictate where you go next in solving this problem. There are two ways that you can find the pH of a buffered solution. One option is you can write the dissociation reaction of HF, right? HF is at equilibrium with H plus F minus, and then make an ice table to find the pH like we did back in chapter 7. I don't know about you, but I don't feel like making any more ice tables right now. And there's a way that we can avoid doing an ice table when we have a buffer, and it's by using this equation called the Henderson-Hasselbach equation. This equation is a shortcut that allows us to avoid the ice table. This is what the Henderson-Hasselbach equation says. It's a very quick way to find the pH. says that the pH of your buffered solution is equal to the pKa of the weak acid that you have in your buffer. I'll remind you, pKa, when you see P in front, that means the negative log of the Ka, plus the log of the concentration of the conjugate base, A minus, over the concentration of the weak acid, HA. This equation is a very important equation. This equation is a very powerful equation because it allows you to very quickly calculate the pH without having to do tons of ice tables and stuff like that. But with great power comes great responsibility. And your responsibility when it comes to using this equation is to make sure that you're aware that this equation can only be used to calculate the pH of a buffer solution. If you try to use this equation to calculate the pH of something that is not a buffer solution, you're going to end up in a very unhappy place. And I don't want to see you in an unhappy place. So please keep in mind that this equation must only be used when you're dealing with a buffer. This is why you must begin the problem by writing out the list of major species and use that list of major species to tell you whether or not you're dealing with a buffered solution. All right, so let's get back to this example. We're now going to calculate the pH of this solution using the Henderson-Hasselbach equation. We're given that the pKa of HF is 3.14. This is on the information page, right? So you don't have to memorize pKa's. All right, so to calculate the to calculate the pH, right? We've got our Henderson-Hasselbach equation. pH equals pKa plus the log of the concentration of A minus over HA. And that's the general form of it, but we can make it more specific to what we're using in this problem. So the weak acid is HF, so we can write it HF on the bottom. And the conjugate base is F minus, so we can write it as F minus on the top. Now let's plug in the numbers. So the pH of this solution is the pKa of HF, which we're given as 3.14, plus the log of the concentration of F minus comes from NaF. NaF breaks up completely in a 1-to-1 mole ratio into Na plus and F minus. So the concentration of F minus is also 0.5 molar. And the concentration of HF, we're told, is 1 molar. The molarities cancel out. And when you plug this into your calculator, what you end up finding is that the pH of this solution comes out to 2.84. And there we have it. That's a really quick way to find the pH without having to deal with an ice table and deal with taking negative logs of H plus concentrations and stuff like that. All right, next thing we'll do is talk about the effect of adding strong bases to buffers.